Today we're talking about the insert algorithm for a doubly linked list. So we're going to learn about this algorithm and how to insert a node by tracing through the algorithm itself. So you can see that I have it already written up there in the upper left hand corner, and we're just going to trace through it and see how it works that way, and we'll finish up with a little bit of analysis at the end. So let's go ahead and get started. So there's a couple of things to keep in mind with this algorithm. One is that it is an ordered algorithm. So it's going to maintain some sort of algorithm. Now, the way that I have the algorithm written right now, we're working with a doubly linked list that is keeping things sorted in ascending order. So an insert and append algorithm aren't going to be compatible with each other because append ignores order. All it does is add new values to the very end of the doubly linked list, right? But with insert, we are maintaining an order. That's number one. So number two, we have to be mindful of all of our references. So our node is going to have a prev reference and a next reference, but we're also going to have a tail reference that we have to keep track of, a head reference that we have to keep track of, and we have to make sure that all of the links in our linked list, all of our references, all of our pointers, all of our variables are maintaining the correct memory addresses. So that is always something that you have to keep in mind when you're dealing with these linked lists, these versions of linked lists. So let's go ahead and get started with the algorithm itself. So you can see that we've named it insert, and there are three things that need to be in scope in order for our algorithm to work. And the first is going to be the head reference. The second is going to be the tail reference. And then the third is going to be the value that we want to be able to insert into our list. So we need those three things. And once we do that, then we're going to have the first part of our algorithm be creating the actual node itself. So we are going to have our head reference, and we're going to have our tail reference, and there's some value. So let's say that we're going to insert 22. So we'll go through the algorithm. First thing that happens is a temporary reference referred to as n is created, and we've got our node that gets created in memory as well. So n is initialized with the memory address of our new node. And then you can see that we're assigning to the variable, in this case we're calling it I, our value. So 22 is going to be assigned to that node. And we set our next reference and our prev reference to null. Right? So that's the first part. That's this part right here. Now the next thing we're going to do is we're going to check to see if we have an empty list. So we can check that by checking the head reference or the tail reference, because remember that a doubly linked list is going to be empty if either the head or the tail is set to null, right? They both have to be set to null when we have an empty list. But for this version of the algorithm, we're just going to check head. So is head set to null? Is our head reference set to null? And we can see in our picture here in this very first scenario, this is an empty list because both head and tail are set to null. So if that's the case, then what do? We set the head reference to n and we set the tail reference to n. So we're copying the memory address that's inside this temporary n reference into our head reference and then into our tail reference. Now what's inside that n reference? The memory address of our node. So that's going to change our picture to look something like this. The head reference and the tail reference no longer point to null. They're now pointing to our new node, and our list now has one node inside of it. Since that was the case, the else gets skipped, and we're done with the algorithm at that point. The n is a local temporary reference, so it goes away, and we're left with a one node list with the value stored, and all of our references, all of our links are correctly updated. So head refers to the node, tail refers to the node, and the node's next and prev references are both set to null. Now, let's say that we wanted to insert 15 into our list. That's our new value. So let's look at how the algorithm handles that. So again, we go back to the first step, which is to create the new node, and we put its memory address in this temporary reference we call n. We store the value, which is 15. We set its next to null, and we set its prev to null. Now we get to the second part, which is the if statement. Is head equal to null? No, it's not, because remember from our first scenario, we added a node. So head now has the memory address of our first node that we added. So we're going to kick down to the else, and we're going to have to do a traversal to find the insertion point, making sure that we keep the links updated and that the value gets placed in the correct order. Remember, the correct order here is ascending. So else, we create a temporary reference called P. which is assigned the contents of the head reference. So we're taking that memory address in the head reference and we're putting it into P. So what's the memory address of that head reference? The head node. Then we're taking another temporary reference, which we will call Q, and we're initializing it to null. So our P reference is going to be our leading reference that is going to be doing the searching for the insertion point. And then our Q reference is going to be trailing one position behind in the list, referring to one node behind P, and it's going to allow us to update that trailing node or that node that comes before the node that we're going to be inserting. We're going to be able to update its next reference by using that Q reference. So now let's look at our loop. While P not null, is that true? No, because as we can tell from our picture, P is referring to the head node. So that's true. And the value we're trying to insert is greater than the value in the node that P is referring to. Is that true? No, because we have 15. So our loop already terminates. It never iterates once here because that second expression is false. So then we have to take a closer look at what our situation is. We go to this first if statement here after the loop. If Q is null, that is true. Then what are we going to do? We're going to update our head reference to N, to our N reference. So this Q here in this particular scenario, by looking at it, if it's null, that means that our P reference never advanced. And so that means that our new node is going to go at the very, very, very beginning. So H gets set to N. So we take the contents of the N reference and we put it in H. And so now our picture updates to this. The head reference is now referring to the 15 node. We skip the else and then we go to the next if. Is P null? No. And we'll see why that test is there in a moment. So since it's not null, we kick down to the else. And so what do? We set P prev to N. So we take the contents of the node that P is referring to, its prev reference right here, and we're going to copy the contents of N. So what that means is that it's no longer going to be pointing at null. It is instead going to be referring to that 15 node. We took the contents of N and we put it in this prev right here, this prev reference. Okay, now what do? We set N prev to Q. What's N prev? That's the node that N is referring to. And we're going to take its prev and set it to Q. Now what's in Q? Null. So all we did was overwrite null with null in this scenario. And then we set N next to P. Well, what's N next? N refers to the 15 node. And then we're accessing its next reference. And we're setting that to P. We're overwriting it with the contents of P. Well, what's the contents of P? The contents of P is the memory address of the 22 node. So our picture updates to this. And then we're done. So since P and Q were temporary, they go away. They leave our picture. And since N was temporary, it goes away and leaves our picture. Now, let's check to see if our links are all good. We start at the head reference and we go down. We follow it to 15. Now that makes sense. 15 is now the first node, so it's now the head node. So the head reference has the head node in it. And then we follow the 15 nodes next. We follow it to the next node, which is 22, which makes sense because 22 comes after 15. And then we follow the 22's nodes next. And that leads to null, which makes sense because it's the last node in the list. So that's good. So from front to back, we're in good shape. Now what about the other direction? We start with the tail reference. And we go to the 22 node, which makes sense because tail is supposed to refer to the last node. Then we follow the 22 nodes prev, and it goes to the 15 node, which is exactly what it should be doing because the 15 node comes before 22. And then we follow the 15 nodes prev, which leads to null, which makes sense because the head node's prev is always going to point to null because there's no node that comes before the head node. So we have success. Now, let us add another node, and this time we will add the value 37. So let's see how our algorithm works in that scenario. So first things first, we create our new node, we assign our value to it, and then we set its next to null, we set its prev to null, and we've got that temporary N reference with the memory address of our new node. Check our first if statement. Is the head reference null? No, because it's pointing to node 15. So we kick down to the else. So we are going to create our temporary pointers P and H again. So P gets set to the head reference, and Q gets set to null. So now our loop kicks in. Well, P not null, that's true because P has the memory address of the 15 node, and the value is greater than what's in the node that P is referring to. That's true because our value is 37. So both of those are true. So now our P and our Q are going to advance. So the contents of Q gets overwritten with the contents of P. Well, what's the contents of P? The contents of P is the memory address of that head node, that 15 node. So then we advance our P to P next. So we take the contents of the nodes next that P is referring to, and we put it inside of our P reference. So what that's going to do is that's going to cause our P reference to now refer to the next node in the list. All right, so then we go back to the top of the loop. Well, P not null, that's true because it's referring to the 22 node and the value greater than the value in the node that P is referring to. That's true. 37 is bigger than 22. So we're going to update the contents of Q with the contents of P. So our Q reference is now going to refer to the same node that our P reference was referring to. And then we update our P with the contents of the next reference of the node that P is referring to. So what is in that reference? What is in that next reference? Null. So the contents of our P reference is now null. So we go to the top of the loop. Well, P not null, false. Thanks to short circuit evaluation, the loop is over immediately. So we don't try to access a variable inside of a node that doesn't exist, because since we're using short circuit evaluation, or because of short circuit evaluation, that second expression doesn't happen. So the P.I doesn't happen. Therefore, we don't get an exception thrown, a null pointer exception, or our program crashing. So the loop is over. So now we go to our series of ifs to understand the situation better. Is Q null? No, because it's got the memory address of our 22 node. So we kick down to the else, Q next set to N. So now we can update that next reference in the node that Q is referring to, and we're going to update it to the contents of N. So what's the contents of N? Our 37 node. So Q next now refers to our new node. So then we go to the next if statement. Is P null? Yes, P is null, because remember that P contained this null value. So what does that tell us? That tells us that we have to update our tail reference. Okay, so since we have to update our tail reference, what are we going to update it to? Well, remember that the tail reference is always supposed to have the memory address of the last node in the list. So that's what we're going to do. We're going to update, we're going to overwrite the contents of our tail reference with the contents of N, which means it's now going to be referring to our new node, which happens to be our new tail node, our new node at the end of the list, right? So now that that's done, we update N's prev and N's next. So that 37 nodes next and prev pointers, what are we going to update it to? N prev set to Q. So the contents of Q is what? It's the memory address of the 22 node. So it's no longer containing null. It's now going to have the address of the 22 node. And then we set it's next to P. Now what's P contain? It contains null. So we're basically just overwriting N next's null with the null that was in P. Okay, and so then our algorithm is done. The P reference goes away. The Q reference goes away because they were local and they were temporary. So those are gone. And then our N reference goes away as well. So let's follow our links to make sure that our algorithm didn't break anything. We start off with the head reference and we follow that to our head node. Still good. Follow our head nodes next, and that goes to the 22 node. Still good. We follow our 22 node, which goes to our tail node. Still good. And we follow up the next of our tail node, and that takes us to null, which is exactly what we need to have happen. So now let's go in the other direction. We start with our tail reference, and that takes us to our tail node. And then we follow our tail node's prev. That takes us to the 22 node, which is what we want. Then we follow our 22 node's prev, which takes us to our head node. And then we follow our head node's prev, which takes us to null, which is exactly what we want. So our algorithm handles that as well. Now, what if we wanted to add a node in between, say, 37 and 22? So we would have a value, maybe something like 29, say. So let's follow our algorithm and make sure that it works. And if it does, we've checked all of the possible scenarios that we have to deal with: an empty list, a one node list, inserting at the beginning of a list, inserting at the end of the list, inserting in the middle of the list. And we are verifying that all of our links in the linked list, in this doubly linked list, remain intact, and all of the values are stored in descending order in our nodes. So we're maintaining that order as well. So first things first, what happens? The new node gets created, and we get this temporary reference n, which is holding the memory address of our new node. We assign the value to our new node. We set its next to null, and we set its prev to null. So just a reminder of what that could look like. If we're talking about Java, then we've got something that looks like this: n next equals null. If we're talking about C++, then we've got something that looks like this: n arrow next equals null pointer. And if we're talking about Python, then we're looking at something like this: n next equals none. So we've got our node created. Is head set to null? No, because it's got the memory address of the head node. So we kick down to our else. So we set the temporary reference p, we set it to head, and we initialize a temporary reference q to null. So our while loop kicks in while p not null, that's true, and the value greater than the value in the node that p is referring to, that's true as well. So the q reference gets updated with the contents of the p reference, thereby pointing to the head node, and then p gets updated with the contents of the nodes next that p is referring to, thereby moving the p reference to the next node in our list. And then we go back up to the top of the loop. Is p not null? True. Is the value we're trying to insert greater than what's in the node that p is referring to? True, because we're trying to insert 29. So then we update q with the contents of our p reference. And so now q is pointing to the same node that p is pointing to. And then we update p with the contents of the next reference in the node that p is referring to. And so now p is going to be referring to 37 node. So then we go to the top of our loop. Is p not null? True. And is the value we're trying to insert greater than what's in the node that p is referring to? No, because 29 is not greater than 37. So the loop terminates, and p and q are in their correct positions. So we checked our series of ifs. If q is null, that's false, because q has got the memory address of the 22 node in it. So we kick down to q next, to the else part. Q next gets set to n. So what's q next? It's the next reference in the node that q is referring to, and we're going to overwrite that value with the contents of n. So n has the memory address of our new node. So our picture is going to get updated to this. And then we go to our next if-else structure. Is p null? No, because p contains the memory address of the 37 node. So then we kick down to the else, and we set p-prev to n. So what's p-prev? P-prev is the prev reference in the node whose address is in p. So we're updating this prev reference, and we're going to overwrite it with the contents of our n reference. So that's going to change our picture to look like this. That 37 node is no longer going to be referring to that 22 node. It's now going to be referring to our 29 node. So then we go down to our n-prev and our n-next, our last two statements at the bottom of our algorithm. N-prev gets set to q. What's n-prev? It's the prev reference in the node whose address is stored in n. So that's going to get set to q. Now what's q referring to? The 22 node, as we can tell by our picture. So we're overwriting the contents of this reference with the contents of this reference. So we overwrote the null with the memory address of the 22 node. All right. And then finally, we're going to set n next to p. Well, what's n next? It's the next reference in the node whose address is in n. So we're setting n next to p. Now what's p? P is storing the memory address of the 37 node. So we're overwriting the null in n next with the memory address that's in p, which is the memory address of the 37 node. Once that's done, our temporary references q and p go out of scope, so they leave memory, and our n reference leaves as well. So now let's finish up by verifying that all of our links still work. So we'll start at the head reference as before, and we'll see that it still refers to that head node. The head node still refers to 22, the 22 node. The 22 node refers to our 29 node, and our 29 node refers to our 37 node, and the 37 nodes next, it refers to null. So our traversal, all of our links are maintained front to back. Now we have to check back to front. So we start with the tail reference, and that refers to the tail node, 37 as it should. We follow 37's prev reference to the 29 node. So that's good. We follow the 29 node's prev reference to the 22 node. That's good. We follow the 22 node's prev reference to our 15 node. So that's good. And we follow our 15 node's prev reference to null. So that's good. So we can see that after that last insert operation, that all of our references, all of our links are maintained in both directions. And so we have a successful algorithm. So now let's do some analysis of our algorithm here and see what its performance looks like. So what do we have? So we've got an operation here. We've got an operation here. We've got an operation here and here. So far that's 4 operations. Now, do these 4 operations change based on how many nodes there are? No, because you only create the node the one time, no matter how many nodes happen to be in your list. Now, let's take a look at our if-else here. Now, in the worst case, we are going to have to do more than just 2 operations. So we're going to have a test here. Remember, when we're talking about big O, we're trying to talk about the worst case scenario. It's not the worst case that we only have to do 2 additional operations if this first operation is true. It's the worst case if we have to go to the else part. Look at all these other statements that we have to deal with here in the else part. So we're going to kick down to the else, and we're going to start counting operations there. So we have to assign the head reference to P, and we have to assign null to Q. So that's 2 more operations that we have to do, and +1 for checking the head reference. Now take a look at our while loop here. Worst scenario is that we have to traverse many nodes until P is null, right? So that means that for every single node, we're going to have each of these tests that have to happen. So that's 2n. But when P is null, this second test doesn't happen. So we have an additional test when P is null. And then for every node that we traverse, we had to update our Q and our P, right? So that's another 2 operations for every node. So we can update this to 2n plus 1 plus 2n, which is 4n plus 1. Now, once our P is at that position here and Q is at this position here, we have to test this right here. Is Q null? So that's a test. So that'll cause us to kick down to our else, which is going to cause us to update Q next. So that's another operation. And then we have to check to see if P is null once that's done. So that's another operation. And then if it is, we have to update the tail reference. So that's another operation. And then no matter what, we're updating n prev and n next. So that's +2 more. So let's add all of those up. We've got 4n plus 1, 2, 3, 4, 5, 6, 9, 13. So that's our big O 4n plus 13. But when you think about it, for very large numbers, what's infinity plus 13? It's still infinity. So we can toss that 13. It becomes irrelevant when you've got hundreds and hundreds and hundreds of billions of nodes, right? Now, when it comes to an infinite number of nodes, 4 times infinity is still infinity. So we can toss this 4 as well. So we can reduce that to a single term, big O of n, and big O of n is linear time. And so that is your insert algorithm.